This is going to be the run through on the Chapter 7 homework. We're going to be looking at qualities of X-ray beams and taking a look at some of the general characteristics that we see when we start working with half value layers and some other concepts. So you'll see here in the first problem where it's asking to plot the following measured beam data and then determine the following. You've got the first half value layer for each beam, then you've got the second half value layer for each beam, and then you've got the homogeneity coefficient, which is represented with the value nu, which is the first divided by the second, and then which of the beams are monoenergetic or polyenergetic. So let's take a look here. Now, one way to take a look at the information here in this particular table is to look at the thickness of the lead that is added, and then look at energy A and energy B, and look at the number of photons that are coming through. Now, what this writing in blue has done has basically taken this and changed it into a percentage as you go down. So it's basically taken each of these numbers and divided it by 10. You can look at this as the number of photons that have come through the lead, and you can plot a graph to see what this looks like. Now, for those of you that have issues with not knowing what software or anything to do this with, or not having a calculator or whatnot, I can provide you with a copy of this. It's just a sort of a homegrown example of what you can do with Excel and graphing. So here for energy A, you've got the number of photons over here, and then you've got the thickness of the lead down here, and the same thing here for energy B. So why do we need all of that particular information? Well, what we're looking for as far as the first half value layer is concerned is we're looking for the amount of lead that's going to cut this in half. And unfortunately, we don't really have a value here listed in the table. So we have to do a little bit of guessing as far as what that value needs to be. So if we go here to the graph for energy A, we're going to look to see where this line, this best fit line here, intersects the value here for 500. And it looks like, if you look at it here, it's about 7.8, which is about what they have. So in other words, the number of photons are going to be cut from 1,000 to about 500 with 7.8 millimeters of lead. Now, that's the first half value layer. What about the second half value layer? Well, we're going to be looking for where it gets cut from 500 down again to half its value again to 250. Now you might be tempted to say, okay, well, the next half value layer is going to be at 20 millimeters of lead, but you got to be careful about that. You got to subtract out the first half value layer from that, the 7.8. So if you do the subtraction there, you come up with 12.2. So reading the graph, we have both of those pieces of information put together. So now the homogeneity coefficient is going to be the first divided by the second. And when you do that, you come up with something around 0.65. Now, when you do the same type of thing for energy B, you can see here it starts out at 1,000. Then we're looking at where it intercepts the 500 line. And if you look here where it intercepts the 500 line, it's just a little before or a little after 11, but they're going to call it 11. And that's pretty close. You could have argued here 11.2, I think, and I think that would have been fine. The second half value layer, again, we are looking at where this thing intercepts 250. which is roughly about 22.2. And if you subtract the 11.2, you would get roughly around that particular value. I would say here we're looking at 11.2. We're looking at 22.2. So if you did the division, I would say it would be roughly around 11 or so. Probably a little bit more. When you do that, you're going to end up with a coefficient that's very close to 1. This is if you're looking for beams that are monoenergetic or polyenergetic. Anything that is closer to 1 is going to be considered more monoenergetic rather than polyenergetic, which is something that as you see the half value layer continuing to increase, it's getting more and more difficult to be able to cut out those energies. Whereas here, if you had one energy, it's going to react pretty much the same way all the way through. So this is going to be considered more monoenergetic, and this is polyenergetic. Now, for the other parts here, we have the first half value layer for a 15 MV photon beam, which is considered polyenergetic. It's going to be 2.3 centimeters of lead. That's the first half value layer. So what is the fraction of incident intensity transmitted through 1.75 centimeters of lead? So we're looking basically for the intensity that we end up with, starting with whatever the initial intensity happens to be. Here at this particular point, we need to figure out what mu is, which we do not have. In order to figure out mu, basically we take 0.693 and divide it by 2.3. We know that's the half value layer, and this is going to end up producing the value of mu. So that value of mu gets put in there. We know what the thickness of X is that we are looking to find out the intensity of. When you put all of that together, you come up with 59% is transmitted through that. It's since the first half value layer is 2.3 and we're putting something less than that, we should end up with a value here that's greater than 50%. The first half value layer for 25 MV polyenergetic beam is 3.8 centimeters of lead. And what is the fraction of incident energy transmitted through 4? It's basically going to be the same process here. We're going to take, in order to find mu, we would take 0.693 and divide it by 3.8. We put that value in, and then we would work this formula down here very much the same way. Take whatever that value of mu is, substitute it in here, take 4, substitute it in here. And we put in 100 here for I naught because we're just going to say the 100% is going to be our original intensity. We should end up with a value here that is less than 50%, and as it comes up to 48.22%, it's something to have a little bit of confidence in. So that's pretty much going to be your homework here.